Okay, welcome back, everybody. Um, so we ended our discussion yesterday with a definition of the cycle index. So let's just remind you um, what it is that's going on. So the cycle index is defined for a group G. Of course, we're thinking of every group as permutations here because that's the context in which this stuff arose. So um, cycle index is defined for a group, and the cycle index of a group that is permutations on n objects. This is uh, this P sub g of the vector x. Vector x contains these variables x1 to xn. Which you could think, right, that the indices here are the labels on the n objects, whatever you want to think about that. This is 1 over the order of the group, or 1 over the size of the group, times the sum over permutations in the group of this m sub pi of x, where this m sub pi was a monomial defined in this way. So this monomial associated to a permutation was defined as this is a monomial in the variables x1 to xn, defined in this way where it is a product of the x's whose indices are telling you the lengths of cycles. So you take the permutation. Any permutation is a product of k cycles. So we went through this yesterday, how even the identity permutation here, you have to actually write out all the one cycles. So any of the cycles, any of those one cycles that indicate which objects are being fixed by that permutation, you have to write them all out for this formulation. That's how this works. So any permutation is a product of k cycles. If we say that its ith cycle has length L sub I, then this monomial is a product of the x's where the indices are the lengths of the cycles showing up in the permutation pi. So there's a very direct way in which this permutation contributes to what this particular monomial is. And then this cycle index is the polynomial I get by summing over the permutations of g, and I'm doing this averaging thing. So I'm averaging, that is, I'm dividing by the size of g here, and I'm summing over all the permutations in g of all these monomials associated to these permutations in this way. Okay, so that seems like there's a lot of layers to this, right? So it's best to do example. Well, tomorrow is now, right? I'm gonna do an example now. Maybe I'll give myself a little bit more room though. So let's give myself more room, and I'll bring this back. Maybe I'll write these two things again. So pi is some permutation in G. It's a product of k cycles. And cycle I has length L sub I. Okay, cycle I is the ith cycle showing up. If we think about this as a product of k cycles, we label those cycles 1 to k, and cycle I is just the ith cycle, right? Reading left to right. So that's the deal. The ith cycle has length L sub I. In this way, the associated monomial to this permutation is the product from I equals 1 to k of x sub L sub I. And then the cycle index is 1 over the size of g times the sum over permutations in g of these monomials. I suppressed the notation here, but obviously these monomials are functions, at least formally, of this vector x that contains my variables, the x sub i's. Okay, so let's do a quick example here. What about if G is the dihedral group on 4 objects? or 4 vertices. What are the associated monomials? So first of all, the thing about the dihedral group is it only has size 8, right? So enumerating every single permutation in that thing is pretty straightforward. There's only 8 of those things, so let's start with the identity. Remember, we have to write all of the cycles now. Yes, it's more annoying than being able to express this notation, but this is required of us. This is going to be what? This is going to be, well, first of all of these cycles. So this permutation here, showing up in this subscript, is the identity permutation. It is a product of 4 cycles, but each cycle has length 1. So in this product in the monomial, this is x sub 1 coming from that cycle times x sub 1 coming from the second cycle times x sub 1 coming from the third cycle times x sub 1 coming from the fourth cycle. Again, all these are x sub 1 because the thing showing up in the subscript here in the index is the length of the cycles, but every cycle in this permutation has length 1. Right, so this is just 4 copies of x sub 1 multiplied together, so this is x sub 1 to the 4th. Okay. Let's do the other permutations. So let's do m sub, we'll say 1, 3 is the permutation, which means it fixes 2 and 4. What is this? Well, this is going to be, so the first cycle has length 2, so this would be x sub 2, times the second cycle has length 1, so that's x sub 1. The third cycle has length 1, so this is x sub 1. So this would be x sub 1 squared times x sub 2. But notice that this would also be the monomial I get if I had this as my permutation as well. So what if I had this thing as my permutation, which is a permutation in the dihedral group on 4 vertices? It would also be this. So let's start boxing these that we're finding. Okay. What about the products of 2 cycles? We can start to think about organizing the elements of the group by how many cycles show up in a product of these things, or how these things can be decomposed as a product of cycles in the normal way using our standard cycle notation. So we have the product of 2 transpositions. 1, 2, 3, 4. Well, because it's a product of 2 transpositions, actually all of these are going to have the same associated monomial. Think about that for a second. Because what matters is how many cycles show up and what their lengths are. Right? So in this case, this is there are 2 cycles show up, a first and a second. Both of them have length 2, so this would be x sub 2 times x sub 2, or x sub 2 squared. And then lastly, there's only 2 more elements in the group to think about, and these are the permutations that can be written as a single 4 cycle. In that case, we get the single term x sub 4. There is a single cycle showing up here. It has length 4, so the only term in this monomial, the only thing that shows up is this x sub 4. Okay. Thus, what is the cycle index in this case? What is the resulting thing? This is 1 over the size of the group, but the size of the dihedral group is 8, so this would be 1 over 8 times a sum over all the permutations of this, which is, I have 1 such permutation here, so that's x sub 1 to the 4th. I have 2 here, So that's plus 2 times x sub 1 squared, x sub 2, plus I have 3 of these, so this is plus 3 x sub 2 squared, plus I have 2 of these as well, plus 2 x sub 4. This is my cycle index for G. Okay. Now, what if I did this for, let's check here. What would the cycle index be for the cyclic group on 4 vertices? I'll leave this for you to check, but this would be 1/4 times x sub 1 to the 4th plus x sub 2 squared plus 2 x sub 4. Okay, so this is just an extra check. Now, by Burnside's lemma, we can actually use this to compute these quantities that we've been talking about. By Burnside's lemma, the number of ways to color n objects using up to m colors, discounting the symmetries of G, is the cycle index with m plugged in all slots. This is in the case of D sub 4. So I'll rewrite it like this, the dihedral group. But let's look at this. That makes P of D sub 4 with m plugged in each variable slot gives me, here, this is what I'm looking at. So this would be 1/8 times m to the 4th plus 2m cubed plus 3m squared plus 2m. Right? Check. If m is equal to 2, then this is equal to 6, just like in the way we computed this previously with Burnside's lemma. Okay. Let's use this to do another example. Okay, so compute the number of 20 bead necklaces so compute the number of 20 bead necklaces composed of rhodonite, rose quartz, and lapis lazuli beads. Okay, so we want to compute the cycle index for the group D sub 20, the dihedral group on 20 vertices here. So you may say, well, in our previous example, doing this for the dihedral group on 4 vertices, I just enumerated every single permutation in the group and just wrote out exactly how they were a product of however many cycles of whatever length, and just directly computed all those monomials, and then that's how I figured it out. So what hope do I have to do that here? Right, I know that there are 40 such permutations because that's the size of the dihedral group. So the question is, how do I deal with that? Surely I'm not going to write out 40 permutations, figure out the monomials for all those things. That would take too long. So what can I do rather than that? So I want to compute this cycle index. How do I do it? So I think about how to organize these permutations, right? So think how to organize these permutations. Okay. So 8 of the permutations are single cycles of length 20. Now, you can think about this organization here. Sorry, hi. So there, now I've boxed this off so it doesn't run together. Thinking how to organize these permutations, I start by asking, well, I'm going to start with those that are like the products of the least number of cycles and then move toward the identity permutation, which is going to be a product, as we know, of 20 cycles, right? It's going to be, the cycle that fixes one, the permutation that fixes one, fixes two, fixes three, so on, fixes all 20 things, so that's a product of 21 cycles. Okay, so, sorry, it sounds like I said 21 cycles, but 20 space 1 cycles, right? So there are 20 cycles, each of length 1, is what I mean. So here I'm going to start with the least number of cycles. So 8 of these permutations are single cycles of length 20. How did I get the number 8 of these? I know that at least some of them are, but the question is which one of them are, or which of these permutations are single cycles? It's more than just one. It turns out it's actually 8, but where does the 8 come from? What are these? These are rotations by 18 times k degrees, where k is 1, 3, 7, 9, 11, 13, 17, or 19. So these correspond to the 8. Okay. Well, since there's 8 of them, and they are single cycles of length 20, the length is the thing showing up in the index, in the cycle index on these variables. So what term do I get? So this gives me the term 8 times x of 20 in the cycle index. That's what this contributes, because there are 8 of these. You can think about how you would determine that there are 8 such things and what causes a rotation to not be writable as single cycle. Okay. Think about this in just the case of 4 vertices is maybe the easiest way to start. Okay. So that's 8 rotations satisfy that. 4 rotations. So 4 of them are products of 2 cycles of length 10. These are rotations by 18k degrees, where k is 2, 6, 14, and 18. Okay. Since there's 4 of them, 2 cycles of length 10, this would be 4 times x sub 10 times x sub 10 is the term in the cycle index, or 4 times x sub 10 squared in the cycle index. Okay. So I'm counting, right now I've counted 12 total rotations. My dihedral group is a dihedral group on 20 objects or 20 vertices. We know that contains 20 total rotations and 20 reflections, thinking of it in the same way. So I've counted 12 of the reflections. I have 8 more total. What about using these different degrees to investigate what the rotations are doing? So what if I have k is equal to 4, 8, 12, or 16? How many rotations is that? Well, 4. These are 4 distinct rotations, and I haven't covered those yet. These are 4 rotations, each which are products of 4 cycles of length 5. So this contributes 4 times x to the 5th 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 to the cycle index, which is 4 times x to the 5th to the 4th in the cycle index. So how many rotations have I counted so far? 8, 4, 4. So I'm at 16. I have 4 more total. I need, what haven't I done here for these rotations? I haven't done 5 or 15 yet. Those can be grouped together. So if k is equal to 5 or 15, so that gives me 2 rotation. In this case, these are 5 cycles of length 4. So rotation, so 2 rotations, each products of 5 cycles of length 4. So this contributes 2 times x sub 4 times x sub 4 times x sub 4 times x sub 4 times x sub 4, which of course is 2 times x sub 4 to the 5th in the cycle index. Okay. What haven't we covered so far? Going through our values of k here. I haven't done k equals 10. K equals 10 is the last one I haven't done apart from the identity. So k equals 10. This is 1 rotation, which is this is 10. So this is a product of 10 cycles of length 2. So this gives me x sub 2 to the 10th in the cycle index. And then the identity, which is k equals 0, 1 identity rotation, which is a product of 20 cycles of length 1. So this contributes x sub 1 to the 20 in the cycle index. Okay. Let's just make sure that we got them all. So 1 rotation, 2 rotations, that's 4. 4, 4, 8. Yeah, that's all 20 of the rotations in the dihedral group on 20 vertices. Now what about the reflections? Okay, so the reflections we can actually take care of basically in 2 cases. So 10 of the reflections, which are the ones through the axes of symmetry that pass through midpoints, are 10 transpositions. The other 10 reflections flip about opposite vertices, and those are those consist of two. They fix they fix the vertices that they pass through. So they're fixing 2 vertices at a time. So 10 of the reflections, so the ones whose axis passes through midpoints of opposite sides, these are 10 transpositions. The 10 transpositions describe how the reflection happens in this 20 gon. But there are 10 transpositions. A transposition is a cycle of length 2. So this is 10 cycles of length 2. So they contribute, and there's 10 of these reflections. So this is 10 cycles of length 2, and there's 10 of them. Right? 10 of these transpositions. So that is what is contributed in the cycle index. And 10 of the reflections, the remaining 10, these are the ones whose axis passes through opposite vertices. Well, since the axis passes through those vertices, it fixes those vertices, right? And so this is going to be, they are, um, these are going to consist of 9 transpositions, and they fix the other 2. And fix 2 vertices. That is 2 1 cycles. When you write that out in the permutation, the 1 cycles will tell you what vertices are getting fixed here. What does that contribute? So there are 10 of these, so this is 10. There are 2 vertices that get fixed, so they have length 1, and there's 2 of them. And then there's the 9 transpositions. The transposition is a cycle of length 2, so this is x sub 2, and there's 9 of those. So that is what is contributed. So then, writing this out, what we have done here very painstakingly is compute the cycle index of the dihedral group on 20 vertices. And this depends on 20 variables in this way. What is this? This is 1 over the size of the group. Size of the dihedral group on 20 vertices is 40, so this is 1 over 40 times x sub 1 to the 20. Now I'm just summing all of those terms that contributed here. 10 times x sub 1 squared, x sub 2 to the 9th, plus 11 times x sub 2 to the 10th, plus 2 times x sub 4 to the 5th, plus 4 x sub 5 to the 4th, plus 4 x sub 10 squared, plus 8 x sub 20. That is my cycle index. And the original question, the number of 20 beaded necklaces that can be made. So when we say number of 20 beaded necklaces, the number of different or distinct with respect to the symmetry, 20 beaded necklaces that can be made using 3 kinds of beads is this cycle index where I have plugged 3 into each variable. Again, this is just direct corollary of Burnside's lemma, that this is what is being computed here. If we do that, I'm not going to do it exactly, but if we do that, we see that this number is 87,230,157. Nicely, of course, generalizable to other related questions that you might be interested in for this stuff. Okay. All right. So that's a good example of the cycle index and how it can be used. Now, it turns out we can use the cycle index to solve more complicated problems than the ones we've been presented with. Okay, so we can use this cycle index to compute answers to much more complicated questions that exist on configurations in the presence of symmetry. So, for example, suppose we need to determine the number of equivalence classes of colorings of n objects using m colors, where I specify a color occurs exactly some precise prescribed number of times. So suppose we need to determine the number of equivalence classes of colorings of n objects using the m colors. We'll call them y1, y2, out to ym, where each color, y sub I, occurs a prescribed number of times. For example, specifically, let's just ask the following question. How many different necklaces can be made using exactly 2 rhodonite, 9 rose quartz, and 9 lapis lazuli beads? So 2 rhodonite, 9 rose quartz, and 9 lapis lazuli beads. So necessarily I'm using 20 total beads, so these are 20 beaded necklaces, but I'm specifying exactly the number of each type of bead that I'm using. Okay. So notice that this is a more complicated consideration than what we dealt with previously. Okay. But at the same time, maybe you have some intuition that tells you that this should somehow be related to this stuff that we've been doing. This should somehow, maybe somehow the cycle index can still be used to deal with this. To solve a problem like this, there is a very useful idea. So useful idea for such problems. The notion of a pattern inventory. So what is a pattern inventory? So the pattern inventory of the different ways to color in objects using M colors with respect to symmetry group G is a generating function in m variables which is the following. So we'll call it big F sub g. It is a generating function in the variables y1 to ym, which means that it is a sum now over m tuples or vectors. I'm just going to write it easiest. I'm going to write it as a sum over vectors v. The coefficient here will be written as a sub v, so the index of this coefficient is actually a vector, times product of these variables raised to differing powers, so y sub 1 to the n sub 1, y sub 2 to the n sub 2, and so on out to y sub m to the n sub m, where the sum is over all vectors v containing these exponents. These are the m tuples I was talking about of non-negative integers satisfying that the sum of those integers is n, and this coefficient, of course, what is that? Well, the point of using generating functions, right? And of course you might complain that, well, we never did generating functions in more than one variable, which is true, but the spirit of generating functions in this way should tell you what this coefficient should be. The whole point of using generating functions in the way that we did was that a generating function for a sequence was just the power series associated to that sequence. The sequence formed the coefficients. But the idea is that the coefficients were counting, right? They were counting the thing that we were interested in. So the whole way that we solved problems using generating functions is whatever thing we wanted to count, we wrote that as a sequence, some a sub k, and then we wrote the generating function for that sequence and worked with the generating function, and the answer, right, to whatever question we were asking was some coefficient of some particular power of x in that generating function. So the same thing is going to hold here. This is going to be counting something we're interested in. What thing is this going to be counting? This is going to be counting the number of non-equivalent with respect to that symmetry group. So the number of non-equivalent colorings of the n objects where the color y sub I occurs exactly the number of times indicated by its exponent. So it occurs exactly n sub I times. So a vector v is this m tuple, contains these n sub i's. The components of the vector tell you how much or how many times the corresponding color appears, okay, in that particular coloring. Okay. So we had this question. How many different necklaces can be made using exactly 2 rhodonite, 9 rose quartz, and 9 lapis lazuli beads? So according to that, using our example here, the answer to the question, here, we'll call this question We'll call this question 1. So here it is on screen again. How many different necklaces can be made using exactly 2 rhodonite, 9 rose quartz, and 9 lapis lazuli beads? Okay, so our answer to question 1 is given by the following. So if we let a rhodonite bead be denoted by R, and a rose quartz bead denoted by Q, and lapis lazuli denoted by L, our answer to question 1 is given by the coefficient of the term R squared Q to the 9th L to the 9th in the pattern inventory, which is F sub D20, because this is the dihedral group on 20 vertices. There are 20 beads in such a necklace. And the colors here are the types of beads, so that's rhodonite, rose quartz, and lapis lazuli. This is the sum over indices I, J, K, summing to 20. These are non-negative numbers satisfying this. Okay, I have a coefficient A sub I, J, K in this way, times powers of R, Q, and L. So R to the I, Q to the J, and L to the K. So I'm looking for the coefficient of this term, R squared, Q to the 9th, L to the 9th. Why? Because that term represents having 2 rhodonite beads, 9 rose quartz, and 9 lapis lazuli beads. The coefficient is telling me the number of non-equivalent colorings of those 20 objects where the color occurs exactly, rhodonite occurs exactly twice, rose quartz occurs exactly 9 times, and lapis lazuli occurs exactly 9 times. Okay. So this is what I need to compute. Now, of course, you look at this and you say, oh my God, that's really, really nasty. So how do I have hope to go about computing this in a way that is reasonable? So Polya noticed the following. Polya noticed that the cycle index can be used to compute the pattern inventory in a nice way. How? Okay, so recall that an occurrence of some x sub k in the cycle index comes from the underlying permutation having a cycle of length k. Okay. If a coloring is invariant under such a permutation, then these k elements must have the same color. So these k corresponding elements must share the same color. So either each k have color y sub 1 or color y sub 2, and so on. Whatever it is, it's all that same color, all k. So then, because of how we treat generating functions, represent this choice. Here's the important bit. Represent this choice as the formal sum which is y sub 1 to the k plus y sub 2 to the k, and so on, plus y sub m to the k. Remember, this was our formulation in generating functions for making choices not in sequence, but this was an OR operation, right? So this plus is an OR operation. Okay. And so it's this expression that we're treating as formally indicating this. What if you substitute this expression for x sub k for each k in the cycle index? So Polya found that plugging this in for x sub k for each k in the cycle index yields the pattern inventory. So this is an extremely nice way of doing this counting that prevents you from dealing with kind of the nastier sort of thing or consideration you have to take into account if you didn't have something like this. Okay, so we can actually use the cycle index to do this for us. The result of this is called Polya's enumeration formula. So theorem. Polya's enumeration formula. Okay. So I'm going to state it just like the textbook states it. Everything's going to be exactly the same. So if you look this up in the textbook, you're going to see the exact same notation, exact same everything. So suppose that S is a set of n objects and G is a subgroup of the symmetric group S of n. As I said here, this isn't restricting yourself very much at all because any group you like essentially can be, we'll say, realized as a subgroup of the symmetric group for some n. Well, all the groups that we're talking about here, all these finite groups that we're discussing. So anyway, let the cycle index be denoted as before by p sub g of x. So let this be the cycle index of g. Then the pattern inventory for the non-equivalent colorings of S under the action of G using colors y sub 1, y sub 2, y sub m is. This is what we used to, this is the notation we use for the pattern inventory. That y is the vector containing the y colors. This is the cycle index for G with these sums plugged in. That is the sum from I equals 1 to m of just y sub I to the first, the sum from I equals 1 to m of y sub I squared, and so on for every power here, I equals 1 to m y sub I to the n. Okay. This is the enumeration formula. Proof. I'm going to not do the proof. It's not very long. It is on pages 203 and 204. It is mostly unpacking this build-up idea, as I mentioned, of encoding this using in the same way we did with generating functions by saying that noticing that any x sub k shows up because of a cycle of length k, a coloring being invariant with respect to that permutation means those k corresponding elements have the same color, whatever that color is. We can represent having that color in this particular case as a choice. This is an OR choice, so we represent this choice as this formal sum. Plugging this into the pattern, or sorry, to the cycle index is exactly what's on the right-hand side here. We just have to show that that is exactly the pattern inventory. I'm not going to do that. If you want to read the proof, it's 203 to 204. Okay, and so how can I use this? So I'm going to give a couple of examples here. So let's do the following. Maybe I'll say it's a quick example. Question 1, right? So what did question 1 ask us again? Let's remind ourselves. Question 1 asked, how many different necklaces can be made using exactly 2 rhodonite, 9 rose quartz, and 9 lapis lazuli beads? So we can compute the pattern inventory using this enumeration formula. Of course, with this many terms, what is the ultimate result of this? Remember, I'm looking for coefficient of r squared q to the 9th L to the 9th. Using this enumeration formula, I can compute the pattern inventory is this thing. Maybe I'll get this closer here. Ooh. Oh, it's not done. It's not done. It's pretty long. It's got a lot of terms. Got a lot of terms, but oh, look at this one. See that term? Oh, well, that term is exactly the coefficient on r squared q to the ninth L to the ninth. So that is exactly telling me the number of ways that I can have this configuration. You scroll all the way up again. So even using this theorem, computing the pattern inventory, right, might be nasty like this, but good news. Computer can do this pretty nicely. This isn't so bad, right? So yeah, it's bad for us to have to write it down or even have to print it in a nicely readable way. But a computer has no problem doing this. And of course, having your computer pick out the coefficient you're interested in that's no problem either. And so this coefficient in that example is 231,260 such ways to make the specified necklace. Okay. Let's see for smaller examples how this actually works. So let's do the pattern inventory of 4 bead necklaces. So pattern inventory of 4 bead necklaces, we'll say using colors red, green, and blue. Okay, maybe so that I don't have to write these annoying uppercase letters everywhere, we'll use lowercase. Red, green, blue here. So according to the theorem, so this enumeration formula implies what? That the pattern inventory, in this case, these are 4 bead necklaces, so symmetry group is dihedral group on 4 vertices. The colors are red, green, and blue. According to this theorem, let me bring it back on the page. I need to define this, or I need to plug into the cycle index this expression. So what is that? This is plugging into the cycle index for d sub 4, the expression that is a sum of all of these to the first power, and then a sum of the squares of these things, a sum of the cubes of these things, and lastly a sum of these things raised to the fourth, and that's where I stop. But what is the cycle index in this case? Well, we've computed it already. Right? So let's go back. What is the cycle index for D4? It was exactly this thing. Okay. So the cycle index was this thing, and I'm plugging in for my vector x. My vector x has 4 slots, x sub 1 to x sub 4. I'm plugging these things in. So what is this p of d sub 4 in this case? I have oh, sorry, here, this one. So I have x sub 1 raised to the fourth, but x sub 1 is just the sum of all of these. This is, so let's just write out what this thing is, combine these things. This is so this gets plugged into the x4 slot. So then this is r to the fourth plus g to the fourth plus b to the fourth plus r cubed g plus r g cubed plus r cubed b plus rb cubed plus g cubed b plus gb cubed plus 2 r squared g squared plus 2 r squared b squared plus 2 g squared b squared plus 2 r squared gb plus 2 rg squared b plus 2 rg squared b. Oh no, I already did that one. That was the last term I did, plus 2 rgb squared. This is our pattern inventory here. Okay. Try this for the cyclic group, where the symmetries you're using are just rotations, not rotations taken together with reflections. Okay. All right. So the idea here, so this idea has many applications beyond simply this immediate application to these necklace problems. Okay, these have applications to chemistry, physics, computer science. In fact, in this paper where this formula was first written out, this Polya's paper, the applications that the most time was spent on was involved enumeration of graphs, trees, chemical isomers, various graphs, trees, chemical isomers. Enumerating various configurations wherever they arise. This has uses in this way. Because I'm running out of time, I think what I'll do is I'll do maybe one more kind of instructive example here that kind of better illustrates what it is that's going on. Then we'll move on from this. I wanted to finish in the course, I wanted to kind of finish with a survey of some other important numbers that crop up. So I wanted to talk about two kinds of Stirling numbers, maybe Bell numbers if we get a chance. Other than that, that's pretty much it. We're rapidly approaching the end of the course, and this was kind of the last big named thing I definitely wanted to get to, was Polya's enumeration formula, which is the payoff for all this group theory stuff we've been developing. And like I said, I think what I'll end with in the last couple lectures is just maybe one more good example of what's going on here, and then talk about Stirling numbers, which arise in other ways in combinatorial problems. So you may have already even encountered these. So anyway, that's the plan. I will post your exam 2 later today, and I'll post an announcement when I do. It'll be due on Friday, the usual time, and that will be the course. So like I said, after today you have 2 more lectures. It will be a nice survey of some interesting combinatorial numbers and maybe another example of this enumeration formula business, and then that's it. That will be the course. That will be all of the graph theory and combinatorics stuff that we're going to do. So anyway, I will see you all tomorrow.